So welcome to the COCO seminar. So today I'm gonna talk about training a model to predict rare events. So I'm gonna talk about a special classification problem today. It is a binary classification where the population of one class significantly outnumbers the population of the other class. So, such as in financial transactions, the majority is of the transactions are legitimate transactions. Only a small fraction of the transaction, are fraudulent, transactions. Same thing in other applications like cancer screening or extreme weather, predictions and so on and so forth. Okay. So in the rest of the talk, I will formulate the problem as a binary classification where the minority class, I will consider minority class as the positive and the majority class as negative. Okay. So today I'm gonna discuss and experiment different strategies to train on imbalanced data set. They are bias adjustment, sample weight adjustment, resampling of the data set, and also a combined sum or the above strategies. And we are going to see which one works better, which one works, what's the effectiveness of each strategy. All right. So normally a classification model outputs a float point value or number that represents a score or a likelihood or probability of being positive. And that float point number is then thresholded to get the final classification. That's the typical way how it works. So because we need to evaluate how good our model is that is trained with different strategies, we must have a way to to measure the performance. So here are some metrics. So first of all, if you compare the model prediction with the actual labeling, you can, construct a 2x2 matrix, which is called a confusion matrix. So here the actual labeling is the rows, and the prediction is the columns. So here TP means true positive. It is the number of positive samples that are correctly classified by the model. And Fn is the false negative, which is the number of positive samples that are misclassified as negative samples. So Tn and Fp are defined in the similar ways. So from the confusion matrix, we can derive some matrix like accuracy, true positive rate, false positive rate, recall, and precision. And the last one is the area under the ROC curve. So for the the skewed distribution problem we are going to deal with today, the accuracy is certainly not a good metric. This is because, for example, in cancer screening, if you let the model, I said, without any training, just let the model output. No matter what is the input, you always classify it as negative. Suppose based on statistics, one after 100 people who take the screening is actually truly a cancer patient. Then by classifying everyone as negative, basically you got you got 99% of accuracy. So, but the model is useless. It classify everyone as negative. No cancer, so it's useless. And the true positive and the true positive rate and the false positive rate, they must work together to give a meaningful measure of the model. Any of a single one of them won't make any sense because you can adjust the operating the threshold to give different detection rate, whatever you want. The true positive rate. But whenever you increase the threshold, you actually decrease the true positive rate. In the same time, you decrease the false positive rate as well. And recall and precision are worked together as well. But all the first 5 matrices depends on the final classification result. And the only one, which is the last one, the AOC, the area under the curve, is the only metric that doesn't depend on the final classification, which means it won't be influenced by the threshold we choose. So that's the main matrix we are going to use for today. So we can plot the ROC curve by gradually increase the threshold from the smallest to the largest, and we can get a sequence of false positive and true positive rate and false positive rate, and we can plot this curve like this. Here, the dashed line represent the baseline model, which is it just give a random prediction or classification, and you can get the ROC under the dashed line, you get 0.5. But for anything, if you train a model does a little bit better job than the random guess, the AUC should be greater than 0.5. The bigger, the better. And ideally, you can get 1. That's the maximum value for AOC. Okay, but in real life, it's really hard to get that good of result, perfect result. So you have to do some compromise. Depends on the nature of the application. Some applications prefer high true positive rate, and in the same time can tolerate a certain amount of false positive rates. So that's something, for example, in cancer screening, but in some others like fingerprint recognition, as a way to log in, for example, into your cell phone, you can tolerate a few, false, positive. That means you try to log in your own phone with your own fingerprint. It rejects you 5 times until you get into your phone. It's a kind of not nice, but you would rather have a 5 or 6 failed login than having someone else log in your cell phone. That's a different criteria. So today We are gonna train a fraud detection model. The data is from Kaggle competition, and the notebook, the original version of the notebook is from TensorFlow tutorial, and I made some modification to it. So let's go to the notebook. Give me a sec. In this notebook, I'm first gonna load the data in and do some preparation, pre-processing of the data, and then I would define a neural network model, very simple one, because today's focus is not about data pre-processing and not about design a better architecture for the model. The focus is to, is focus is on the different strategy we're gonna employ to train on imbalanced data. So I'm gonna use I'm gonna experiment those strategies, and so let's do it today. So first we load in some Python modules like TensorFlow, scikit-learn, so on and so forth, and we I'm gonna make the process repeatable. So I have to move this one away from here. I'm gonna, set random seed. After that, I'm gonna load the data. It's already saved in a CSV file. I'm gonna load it in and take a quick look of the first 5 lines. You can see that it has features like V1 to V28 plus time and amount. And the last one is the most important one called class. The column class is the label, whether or not it's a fraudulent transaction. 0 means it's legitimate. 1 means fraudulent. Okay, so we keep going. So we get the summary of the data frame. We just load it in. We see we have we have a 284,807 entries, and we check each column. We see there's no missing data. That's good. All the features are float point data, except the last one, the label, is integer. It's either 0 or 1. And we then do a bin count to count on the class to see how many, we see we get, 492 positive samples after the totals. So that means that it's a very rare. It's a highly skewed distribution between positive and the negatives. And after that, keep going. All right. So, like I said, I'm not going to spend a lot of time on the feature engineering or something. I just do some quick dirty work for the in the data pre-processing step. Basically, I'm gonna remove the time. I think time is useless. And also I take a log scale of the amount. I think amount probably the amount of in terms of a currency or something, but it doesn't matter to me. I don't care. So I take a logarithm of that. That's all. That's all I do for the data pre-processing. After that, I'm gonna split it into three subset: training, for testing, and evaluation. So in the end, I have a train validation and the test input and the train labels, validation labels and test labels. Those are the things that I have. After that, I'm gonna do so-called scaling. So it's a way to normalize those features. Up to now, because I discard the time feature, I have 29 feature left. So here I'm for when I use the standard scaler, which means after the scaler, I actually do a shift and the scaling together. It makes the result with or has a mean at 0 and the standard deviation equals 1. That's what it does. I actually tune the scaler on the training set and apply to other site like validation and test. And after that, I'm done. I'm finished. Here is the summary. You can see that I have a training sample 182,276 samples. Each has 29 features. And yeah, and this one is the labels. We are ready to go. So we did a final checkup to see the percentage of the positive samples. We can see they are not, because we just randomly split the training set. It's not going to be even. So we see the training set has a slightly less positive rate than the positive sample the percentage is less than the percentage in validation, but it's quite around 0.0018, something like that. So that means out of 1,000 samples, we expected to have 1.8 positive samples, like either 1 or 2. Yeah, that's a ballpark figure of the statistics. All right. So here I'm gonna use, like I said, the area under the curve, and I also use cross entropy and accuracy. Although I said accuracy doesn't mean too much in such a classification problem, but still I'm gonna use it. And then I'm gonna define a model. I'm using this function make model. And you can see basically I define a 3-layer, 2 dense layers. In between, I have a dropout. Dropout is just a kind of regulator layers that are used to overcome the overfitting problem. So basically, it's just 2 layer of dense layer, 2 dense layers. That's all. And yeah, so that's it. But we have an option to pass in a bias. The bias will, if it's not none, we will create a bias initializer based on the bias value that we want to put in, and that bias will be used in the last layer, last dense layer. We are gonna use it here. Okay, I'm gonna talk about that later on. So after that, I just compile it, and I'm gonna use the cost entropy as the loss, and yeah, that's it. So let's run this one. All right, and keep going. So here I'm gonna make our first model. Just call the make model function. It will return a model, and I'll do summary. I can see that this is the structure, dense layer, dropout, and the dense layer again. And then I'm gonna define the size of the batch to be 2048. Why I choose this number? Because this will give us approximately three, maybe a little 3 or 4 positive sample in each batch. But if we are not lucky, probably in some batch there's no positive sample at all. It's possible. And so we want to, let's say, do a prediction. Even though we haven't trained the model yet, we want to see what the model will give us. So we train it, and we see that this is the output. We see basically the output is, half around 0.5. So that makes sense because we haven't trained the model yet. So it's quite neutral, means it has the zero bias. That means it, to declare either positive or negatives. And if we evaluate the model without training to see what's the loss. So loss is 0.76 or 0.77 or something. And next, we're gonna, change the bias. Why we do that? Because here we want the output to be, give the similar, distribution to the true distribution of the data. Like most of the data samples are negative, but here is half. So we want to change that. There's some math. We do the inverse of the calculation. We know that the bias B0 should be logarithm of the number of positive over number of negative. All right, so we just did it. So we calculate it. We see, okay, we need to set our bias. The value is minus 6.335 or something. So what we did is we load we make the model, and we in the model we give the bias that we just calculated, which is minus 6.35, and now you can see the result. When we apply the model without training on the first 10 samples in the training set, we got pretty good, because it declared most of them, negative if we choose 0.5 as the threshold. Okay, so let's calculate the loss. You can see that, okay. Oh, I should click here. Okay, here. So you can see that basically here we have, based on theory, it should be 0.0131, something like that. Let's check the real value. We just run it, and let's see. It gives a value very close to the one. It's just like it's very close to the ideal theoretical result. Okay. All right. So that means by setting the bias without training, we already reduced the loss, to this number 0.011 or maybe 0.0112. Compare that to what we have before, 0.77. Okay, so we significantly reduce that number. And how about we train it? But before we train it, because we need to make a different kind of comparison, we want to fix the weights. So what we do is we first take a snapshot, saving the weights of the neural network. into a file called this one, and later on we can load it in. Because without training, most of the weights are initialized randomly. Only the BIOS that we give in this number. That's what we get. The rest of the trainable parameters are initialized with random numbers. So we take a snapshot of this one. We are gonna, confirm that BIOS really works by training it. So we train it. So you see these two blocks. The only difference, the first one we make a model, load the weight from the snapshot, and then we assign the BIOS back to 0, because in this initial weight, the BIOS has already adjusted. So we're gonna go give it back. So the only difference is the first block has this line to set the BIOS to 0, and the second block doesn't have that line. So the second one use the BIOS correction. So let's see the result. And let's run this one. A little bit slower than I expected. Okay, and I run again. The second one, the one with so the one without BIOS, I got the last year. I just want to check what initially this BIOS should be 0. But after training, it got some number like minus 0.5 or something. But for the original one, we set the BIOS to -6. It doesn't change too much, you see. So we train these two models, one with the other without BIOS correction, and the result are in the history. One's in here, the other is in here. So we're gonna plot this one to see what we have. So we define the plot function and we plot it and see this is the result. So you can see the red is the one without the BIOS adjustment. You can see the blue one converge faster than the red ones. So that's a proof of the BIOS correction helps. Okay. So next, I'm gonna train the model with a lot of more iterations. So I define the maximum one is 100, but I can do an early stop by watching the area under the curve that was measured on the validation dataset. So let's do that. I define that and let's run it. So it stopped at 37 epochs, but he found the best one is 27. If we check the this value, 27 is this one, 27, and we got 0.96 is the best one. Yeah, that's what we have. So that's the best one, we got, and we're gonna plot the history. You can see we plot the loss and the AOC and the accuracy, and that's the model that we just do the training without weight adjustment. We just do the BIOS adjustment. All right. So then we are gonna evaluate the trained model on the test data. So we run it on the test data, and we're gonna, check the result of the ROC on the test data. So you see the test data, we didn't get a very good result. That is not as good as the one that we get before, like 0.96. But here, when we evaluated on the test data, we got below 0.994. So that because each data set has different configurations of the samples, and also because the test set doesn't have too much positive sample, like if I remember, kind of below 100. So there's a lot of unstable calculations there. The statistics is not very stable, so that's understandable. So next, I'm gonna plot the confusion matrix by choosing different threshold. Like I said, the model output a float point number representing probability. I'm gonna, threshold it at different values. First threshold at 0.5, and then take smaller and even smaller threshold. So we got 3. So by taking threshold at 0.5, I got 74 true positives, and 19 positive samples are misclassified, and at the cost of only 6 negative samples are misclassified as positive. So that's it. If we change the threshold to make it smaller, so we will have a higher detection rate, like 80, but at the cost of increase of false negative. And the same thing here, false positive, sorry. So the same thing, when we just increase 1 more from 80 to 81, we have a lot of negative samples are classified as positive samples. So that's the nature. And then we are gonna plot the ROC. So here is the ROC curve of our first model that use BIOS adjustment, but without that. That's the only strategy we have used. Next, we are gonna apply, class weight adjustment. So first of all, we are gonna, make the contribution from the positive and the negative are equal in each iteration. I mean, equal in terms of statistics. So what we do is we first calculate the total number of samples, and then I calculated the weights that I'm going to apply for the negative sample by using this formula. So the sum of the contribution from the next sample should be equal to the sum of the contribution from the positive sample based on the weights. So I would mention that if you, without specifying weight, like I did when I trained the previous model, the weight is default to 1, but here it could be some different values. So after we do the calculation, we can see that the weight that I'm gonna used for the next sample is 0.5. For the positive sample, each positive sample I'm going, the weight is 289. So it's a lot bigger than the negative sample. But consider that there is only a few positive samples in a batch. So this will balance the contribution from the both classes. All right. And the same thing, I'm going to use the same early, stopping strategy. And when we train the model, this time, I'm gonna supply the class weight. The class weight we just calculated before here. We just calculate. So the class weight is actually a dictionary. The first one, it's dictionary from the class label to the weight. We have 0 and 1 as labels, and these two are the weights for negative and positive. Okay, so next we're gonna train this one to see what we have, what we get. So the best result is from epoch 57. So let's go back to where is it? 57 is here, and the best value is 0.9868. So that's the best result. And then we do the same thing. We just plot it. And then we are gonna, evaluate it on the test data. And, we see that when we evaluate the area on the curve on the test data, we got a result of 0.98. 97, not 98. So slightly smaller than the one we have here, but it makes sense because when you're training, you monitor and choose the best result on the validation set. But here, maybe the optimal result for the test data is somewhere not at epic 57, maybe it's at 37 or maybe 67, who knows. So so that's explainable, but very close. And we're gonna plot the confusion matrix for using different threshold, and we can compare. But from this one, you probably need only if you compare this model with previous model, probably you only consider the threshold at 0.5. So here we got the 80% of correct clarification at the cost of 773 features classified as negative, some classified as positive. So that's cost. So it just means we operating at a different point of the curve, and then we do the plotting. We plot the previous one with the current one. We call previous one baseline model. The current one we call it a model trained with weighted samples. We can see that in the early part, let's say at the true positive rate, below 90 or before 88 or 89, the weighted strategy works better than the baseline. And then the baseline works better in the middle range. And after that, at the higher detection positive rate, then the weighted strategy wins. You see, it wins. That's what I interpreted. So you can also interpret it based on this value, which is the ROC curve evaluated on the test data by using the weighted model, and the previous one I used the baseline. So this one is 70, no, sorry, 0.97. Let's check what's previous one we got. Previous one got 0.937. So that's a big improvement in terms of AOC. Next, I'm gonna check the last strategy. It's called resampling. You can either downsample the negative samples and or you can oversample the minority class. So here I'm gonna oversample the minority class. What I did is first I calculate the I separated the training sample into two classes. One is a positive sample and negative sample, and their corresponding labels. And after that, I'm gonna choose. I'm gonna increase the number of positive sample by 10-fold. So that's what I did. So let's run it. I do this and I do that. So after that, you can see the feature of resampled positive samples is 3,130. But before I do the oversampling, there are only 313 positive samples in the training set. So it increased 10 times. Okay. And then what I'm going to do is I'm gonna put back the resampled data with together both the positive and negative and merge them together. And finally, I got my resampled input. And okay, let me see. Yes, I got my resampled input and output. So these two are what we need for the rest. So if you compare what the resampled with the not resampled, you see we have an increase like roughly 3,000 something. That's what we did, maybe close to 3,000. Okay. All right. So let's train on the resampled data, but we still need can play with the weight. Instead, you can either use 0.5, 0.5, which means they equalize their contribution. You can also, play different number. So here I more emphasize on the negative sample, less emphasize on the positive sample, but it's just a balance. You can check experiment with different numbers. So let's see what we have here. So let's do the training. So the best one is 31. As 31, let's see, 31, we got 0.9866, pretty close to previous one, but that's the number we evaluate on the validation data set. So we so first plot it, doesn't matter. Then we evaluated on the test data to see what we got. We got this one pretty close to what we got from the weighted sample strategy. So similar, and yeah. So let's plot the ROC curve. Oh, sorry. Yeah, we should do this one as well. And then do the last one. So we plot the three models we trained with different strategy. The red one is trained with only the bias adjustment. The blue line we train with bias adjustments plus the sample weight adjustment, and the green one we add the another strategy, apply another strategy on top of those two, which is resampling. Of course, there's a lot of numbers that we can play with, like what's the oversampling rate? I choose 10, how about 20 or some other number? Also about later on, after that, I play with the weights. Either it's a half-half or eight versus 2 or whatever. There's a lot of room to play. But from this plot, you can see the green one on average is pretty good in overall, but not significantly. So that's my conclusion, based on the experiment. But I would say the evaluation numbers we got from this specific data set may not that certain. Probably we should test these three strategies on other data set, especially some larger data set, to make a confirmative conclusion. So, but anyway, if you later on you are dealing with similar problems, you can apply those strategies and experiment to see which one works better, and so on and so forth.